We would have bases on the moon. People would live and work on the moon. We would have colonies on Mars. It'd probably be mostly researchers, but there might be tourist opportunities. It would open up space to the average person. Hi, I'm Mike Palushek. I'm president of Princeton Satellite Systems. We've been in business since 1992. Our focus has been on space and energy technology. We started by working on spacecraft control systems. We started developing software products for spacecraft design and analysis. And then we branched into energy and propulsion. We have been working with the Plasma Physics Lab since 1998 on space propulsion, starting with just plasma propulsion and then moving into nuclear fusion propulsion systems.
And so we were interested in meeting up today specifically on your designs for fusion propulsion. So
Okay.
could you say a little bit about, well, first of all, let me ask you this. Why do we need fusion rockets? Why can't we just continue forever with the chemical propulsion?
The chemical and electric propulsion systems have proven to be great propulsion systems for the missions we've done to date. They got us to the moon. We've done a lot of robotic exploration of Mars, missions all over the solar system, and they've been a spectacular success. The problem is that missions that you might want to do, which require delivering bigger payloads to the outer planets, going into orbit about outer planets, interstellar missions, or sending a lot of people to Mars, really would need better propulsion systems.
And one of the reasons you wrote a paper about is getting people to Mars faster.
Right. One of the things about getting people to Mars is that you would like to get them there faster to minimize damage due to radiation. There may be several different mechanisms which radiation is bad for astronauts. We want to mitigate that by getting them there faster. That's the simplest way to do it. Alternatives are more shielding and things like that. The other thing about going to Mars with a more advanced propulsion systems is you can get yourself away from the launch window problem. For example, if right now with a Hohmann transfer, there are only certain times in which you can go to Mars. With a system that did not require the coast trajectory of a Hohmann, you can get there, you can go there almost any time you want it. This leads to one of the critical things needed is an ability to abort a Mars mission. If your astronauts get sick or the spacecraft develops problems, you want to get back from Mars quickly. And you can do that with a system which has a lot more velocity change capability. And that would imply something which has both reasonably high thrust. And we're not talking about like a launch from the Earth. We're talking about 10 to 20 newtons for a spacecraft that humans might be on. And enough power to get them back so you don't have to use a lot of fuel to do that. But that's a critical aspect of any kind of mission to Mars. Look at Apollo 13. They were able to return to Earth. Suppose they couldn't have returned to Earth. They were halfway to Mars. What would have happened then?
Right. So it sounds like you have a lot more degrees of freedom.
Correct.
And then also you had written something on a mission to Pluto, or taking the mission to Pluto as an example of the kinds of things
Right.
the fusion rocket could do.
Yeah, we were very excited about the New Horizons mission, which produced tremendous science. It was a phenomenal technological achievement in a very small package. And it flew by Pluto very quickly and got a lot of data and is sending back to Earth very slowly. Now we thought, well, gee, wouldn't it be much better if we can go into orbit around Pluto? Well, how do you do that? People have proposed fission electric systems. That was done like in the early 1990s, a nice NASA paper. And we came up with the idea for a fusion system which would produce thrust directly from the fusion reaction, not first converting into electricity, and then going to Pluto takes about 4 years, then going into orbit, and then using the fusion power plant, switching it to power generation mode to power a lander. So you'd be in orbit around Pluto, you'd be able to send a tremendous amount of data back because you have so much power, more or less the amount of data you can send back is proportional to power. And then you, again, use it for scientific experiments in Pluto orbit and on the surface. Powering the lander was just the idea. It's been thought of, it's like the space powering from the Earth. You just transmit power via laser beam to, essentially it's a solar array, but you would then call it a power array to power the lander. And as you pass over it, you power it, store it up in batteries, and do surface operations and recharge every once in a while.
So could you say something about the fusion rocket that your company has designed?
Right, it's based on an invention by Dr. Samuel Cohen of the Princeton Plasma Physics Lab, which is probably the world's leading center on fusion research. They were the first center, I believe, to generate fusion power from a tokamak back in 1995, the tokamak fusion test reactor. And this machine is different geometry. What it is a closed magnetic donut inside a solenoid. So it's very simple. So you have a solenoidal coil, which is producing magnetic field, maybe 5 to 7 Tesla. And inside of it, you have a closed magnetic geometry generated by having magnetic fields rotating around, essentially antennas, which cause a plasma current to form. And that's where the fusion happens. Now it's very small, and one reason it has to be small is because the depth of the radio frequency penetration of plasma is limited. So if we had a big machine, we wouldn't be able to heat the whole plasma. So that's one reason to make it small. Another reason is that we want the products of the reaction to leave. Our baseline fuel is deuterium helium-3, which is considered an advanced fuel. That reaction itself does not produce neutrons, but because you have deuterium in the plasma, you're going to get some deuterium side reactions. Those do produce neutrons, and they produce tritium. You really don't want the tritium to fuse, because then you get really high energy neutrons, and you're back to the DT reactor, which has all sorts of material problems. In our machine, it's small enough so that the tritium spirals out and is basically flushed out of the engine, so it does not react. And that gives us a very, very low neutron production and less damage to the reactor, so we hope to be able to get the lifetimes needed to do a mission like to Pluto.
Mm-hmm. And then it's the charged particles from the reaction and also some deuterium that's inserted that becomes the thrust.
Yes, that's correct. We produce thrust directly. The charged particles leave the reaction. They essentially mix with additional deuterium flowing around the reactor in the scrape-off layer, and that goes out through a magnetic nozzle and generates thrust. And we have to recycle the power that comes out of the reactor due to X-rays and synchrotron and waste heat in order to drive it, because this is a driven reactor. In other words, a driven reactor is one in which the reaction itself does not self-heat. So the products do not give any heat to the reaction, or very little, and we have to drive it, and that's what our rotating magnetic field does. It drives the reaction itself. So we have to recycle it, convert to electricity, and convert it back into RF power.
So how soon can we have a fusion rocket?
Well, we think it would take us between 5 and 7 years to demonstrate fusion. We have not demonstrated it yet. Our current experiment, which is PFRC, Princeton Field Reverse Configuration number 2, has been in operation for a few years. It's getting really good results, but it doesn't have the kind of plasma densities and power levels and temperatures to produce fusion. We want to build another machine, PFRC3, which would actually demonstrate fusion. Now that would be a plasma demonstration. Ideally, in parallel, we would develop all the subsystems so that at the end of the 5 or 7 year period when we demonstrate fusion, we'd then be able to go to a production of at least a terrestrial test bed in a few years after that, and then to a space reactor.
So something in the range of a decade or so.
A decade would be reasonable, yes.
Mm-hmm.
I mean, a lot of it is dependent on the funding and how sustained the funding is. And right now we have NASA interested. We have 2 STTR grants from NASA working on subsystems. One is on the radio frequency heating system. The other one is on the magnetic coils. And in this case, we're looking at high temperature superconductors, which will make the machine less expensive and hopefully less massive. And then we have a NIAC Phase 2 grant to look at detail and more of the fusion aspects to support the Pluto mission.
Now you mentioned helium-3 as one of the fuel components.
Right.
So when we were speaking before, you said we can get helium-3 through the processing of tritium.
Right.
But there's also a helium-3 source on the moon, an abundant one, and a source in the atmosphere of some of the gas giants and
That's
so
right.
forth. So can you talk a little bit about that?
Sure. I mean, there was really good work done by the University of Wisconsin showing that it is feasible to mine the moon and bring it back economically, and they did an economic analysis. And the technology isn't a whole lot different from what we used on Apollo. We know we can land on the moon and come back. In fact, you can think of the astronauts as being the first helium-3 miners, because they bring back a little bit of helium through in the rocks they brought back. So that's great. So that's one way to do it. The gas giants have enough helium-3 for ever. And if you were to develop these fusion-powered rockets, which we're talking about, then it would be practical to go to the gas giants and essentially mine the atmosphere for helium-3. So there'd be essentially unlimited amounts. Once you have this kind of transportation capability, there are lots of things you can do you just couldn't even imagine doing now.
I have two more questions for you. One, so your design for a fusion rocket, let's say, is sort of a first generation fusion rocket.
Yes.
What might the advanced fusion rocket some decades from now look like or be like?
Well, hopefully the specific powers would go up, so we can do even more ambitious missions. For example, if you wanted to go to a nearby star system, you need a specific power much, much, much higher than we think we can get now based on our engineering estimates. So that's one thing you would be able to do.
And your company has a paper, an idea of going,
Yes,
using that to go to a distant star
that's
system.
right. We actually have in the Tennessee Valley Interstellar Workshop coming up. We'll be presenting another paper on that. In fact, our first fusion rocket paper was at the DARPA 100-year Starship Conference, where we talked about going to Alpha Centauri. So, and our idea is not just to fly by, but to go into orbit and say hi to anybody who's there.
So, my last question is, obviously fusion rockets, this is not just an incremental improvement over chemical propulsion, this is a leap to a next
Right.
level. So with that and with the accompanying space infrastructure like cargo infrastructure and so forth, what could humanity's future look like in a few decades?
Well, you remember the movie 2001: A Space Odyssey? It would look pretty much like that. We would have bases on the moon. People would live and work on the moon. We would have colonies on Mars. It'd probably be mostly researchers, but there might be tourist opportunities. It would open up space to the average person because there'd be a lot more opportunities to move places in the solar system. It would be a lot less expensive. So ideas of going on tours around the moon or going to Mars would be feasible. You would have a lot more robotic exploration. We'd probably have orbiters around all the gas giants, and these orbiters would have a lot of power. They produce a lot more science. It would be routine. We'd have um, missions to the 550 AU point where you could use the sun as a gravitational lens to see images of planets and other solar systems at about the resolution as you see the Earth from geo orbit. And you can imagine how exciting that would be to be able to see to that level. And this, we could explore the nearby galaxy doing these things. And we could begin exploration of interstellar space. So all these things would be possible. And it would also make it possible to do things like mine the asteroids and actually make money doing it. Some asteroids with certain metals are economically valuable, and mining them makes sense, but you have to be able to get the materials back at a low cost. And this would allow that to happen. So essentially, we'd be really industrializing space, something people have talked about, but really hasn't been feasible when you're limited to chemical propulsion and maybe fission, thermal, which is an incremental improvement over a chemical that would future lunar missions, had the Apollo program kept going, would probably have used a nuclear upper stage, fission upper stage, and we tested it, fired them in the desert. But that's again an incremental improvement. So this would open up a lot more possibilities. And with more and more commercial space happening, I think that there's a lot of excitement and people want to get involved in this, and this would broaden their opportunities to get involved in space exploration.
Great. Thanks very much.
Thank you.